Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Good afternoon, everyone. So this week we're going to add some complications to our multiple linear models, right? So until last week we looked at fitting a multiple linear model where all of our predictor variables were essentially quantitative. They were measured on a number scale. Okay. This week we're going to focus entirely on having some of our predictors as categorical variables, right? So what happens to a multiple linear model? How do you interpret such a model? How do you fit such a model when you have some variables which are categorical in nature, right? Now, before the break, we had looked at an example of what essentially happens, right? So when you have a categorical variable, visually you can sort of treat it as a model which has multiple lines with different slopes and intercepts, right? So that's what, in a sense, fitting categorical variables is like. But before we get into the nitty-gritty of all of that, let's look at an example of so we'll continue working with the housing data example from last week, okay? You'll notice that last week we had a small data set which essentially had 4 variables. Our response variable, which was price, and then the predictor variables, which was the number of bedrooms, number of bathrooms, and the living area size, right? So square foot, living area as measured in square feet. Today we're going to look at an extended version of that same data set where we have some other variables recorded as well. Okay, again, this data set's available on Waddle. Okay, it's called KC housing data. Okay. So what I've done here is saved it in a data set or a data file called h.data. Okay, and you'll notice in particular the extra number of variables we now have, right? We'll look at some of these, not all. Particularly this week we're going to focus on this variable called waterfront, okay, and another variable called condition. Okay, both of these are categorical variable, right? Waterfront, as the name suggests, essentially measures whether a house in that data set is in front of a waterfront or has a waterfront, right? So if it does, then the waterfront variable takes on the value 1, okay? And if it is not on a waterfront, then waterfront variable takes on a value 0, okay? So although the codes or the data is stored as numbers, those numbers do not have meanings of 1 and 0, right? They're more to represent one category versus another. And 1 is the presence of a waterfront, and 0 is treated as an absence of a waterfront for that property. Okay. Condition is also a categorical variable, but it has more than 2 categories, right? So it's a multiple category variable, and we'll come to that later on, most likely tomorrow. Okay. Now, if you wanted to understand how price reacts to being on a waterfront, we can sort of test, or we can observe that relationship, right? Firstly, a few things to note about that variable. Again, this is mostly revision. You would have done this in a lot of your introductory stats courses, but we'll quickly run through that so that it sets up the regression exercise that we actually want to get to. Okay, so looking at the waterfront, you'll see the variables, the values of that variable are either 0 or 1, okay, as we can see using the unique command. Right? The unique command essentially lists all the unique values that are stored in the variable waterfront. Okay? As you can see, that's just got two values, 0 or 1. Okay. Here's a box plot. Now this is a box plot of the price variable, right? So we want to see how price differs between properties which have a waterfront versus properties who do not have a waterfront, okay, which do not have a waterfront, right? So the box plot is of the price variable. In particular, it's of the log of price. Okay, remember in our multiple linear regression models, we worked with the log price as our response. Okay, so we had applied that transformation because that makes the price much more, it fits in nicely with all the assumptions that we need to make for our regression. Okay, so over here, log price, you can see there is an obvious difference between the log price of properties which have a waterfront versus properties who do not have a waterfront, right? The orange box plot is the ones which have a waterfront, right, as denoted by the value 1, and the blue one represents the one which do not have a waterfront, okay, which is sort of expected, right? Properties which are on a waterfront are more valuable in general, okay, and that's sort of reflected in that box plot. Okay, now in Stat 1008 or any other earlier stat courses, so 7055 or something like that, you would have looked at a two-sample test to statistically test whether that difference that we observe visually is actually statistically significant, right? So the test that you essentially perform, okay, you can write it out as these hypotheses, is that the means of the two groups, properties with waterfront versus properties without waterfront, okay, is equal, right? So your null is, sorry. So your null hypothesis is that the mean with waterfront, mean without waterfront is equal to mean with waterfront. Okay, so mu 0 and mu 1 represents the mean of the log price variable, or for that matter, the price variable, where waterfront is 0 versus where waterfront is equal to 1. Okay, as just shorthand notation to write that. Versus the alternative that it should have actually stated, that equation should be not equal to. Okay, so just make that change. So the alternative is mu 0 was not equal to mu 1. Okay. Similarly, you can write the same hypothesis slightly differently, in that we say that the difference is 0 versus the alternative that the difference is non-zero. The difference in the two means. Okay. Pay particular attention to the fact that we are choosing an alternative where we are not really concerned about which one is higher and which one's lower, right? Just that they are unequal. They're not the same. Okay. An alternative that you can choose based on what you've observed and what sort of practical, for all practical purposes, we would assume or expect to happen, right? So another alternative that you could have chosen was that mu 0 is less than mu 1, right? The mean prices of without waterfront properties is less than the mean price of with waterfront properties, right? Okay, you can carry out this test again. These formulas and the test, the t-test, the details you can easily find in your earlier stats courses, right? You calculate the test statistic, over here denoted as T observed or T OBS, okay, which is essentially the difference between the sample means, right? You divide it by the pooled standard deviation, right? The pooled standard deviation of the two groups. Okay. Again, the formulas and so on, I've listed them here, but more details are there in your previous stats work. So if you're confused, if you've forgotten, I suggest you go back to that and have a look at that. Okay. We can obviously use, for us to evaluate this test statistic and therefore complete this test, we can evaluate the various different required values, so y bar 0 and y bar 1 and so on, using R, right? So y bar 0, which is the sample mean of all the prices, or essentially log prices, where waterfront is equal to 0, okay, can be calculated using this function. Right, so essentially calculating mean of the log of the price, right? Okay, but with the condition that you only look at those price values where waterfront is equal to 0. Okay, so this particular way of writing these conditions out, and you should start getting familiar with that. Whenever you be dealing with categorical variables, these functions are quite useful. Okay, so you're essentially testing whether waterfront is equal to the value 0. Okay, and that's why you see the double equal to sign. Okay, if you write a single equal to sign, it is assumed, or R treats it as an assignment. Okay, so basically you're saying waterfront equals, set waterfront to 0. Okay, but if you want to test whether waterfront is equal to 0, you put in the double equal sign. Right? Does everybody get that? Right, that's just your R tip. But getting back to this, we calculate the means of the log price variable. Okay, one for the group where waterfront takes on value 0, and another one for the group where waterfront takes on the value 1. Okay, so these would represent the sample mean of log price, okay, but for the two groups separately. Right? You can also evaluate the length of these samples, okay, how big those individual group samples are, or the group sizes are, and you can evaluate the pooled standard deviation as well. Right? We just using this formula above here, okay, and just fact code that into R, and you can get the pooled standard deviation. Once you have all those elements, again, you can calculate the observed statistic based on that formula. Right? Notice, in this case, mu0 minus mu1, okay, which are based on your population data, okay, which you obviously don't have the value for, but you set the value for mu0 minus mu1 based on the assumption that null is true. Right? So if null is true, then mu0 and mu1 must equal, therefore that difference, mu0 minus mu1, must equal 0. Okay? So that's how you would calculate your T statistic. Okay? These are the obvious, all the different values that we just calculated. Right? So y bar 0, y bar 1, n0, n1, and the pooled standard deviation. And therefore observed statistic would be, so that's y bar 0 minus y bar 1 minus mu0 minus mu1, which is 0, over pooled standard deviation. Okay? Right? So once you get your test statistic, you need to compare it to an appropriate T distribution. Okay, and for a two-sample t-test, mean test, the T distribution cutoff value is based on a T distribution with n1 plus n2 minus 2 degrees of freedom. Okay, the two samples, the two groups that we have both sizes of, have both sizes of n0 and n1. Therefore, the combined degrees of freedom is n0 minus 1 plus n1 minus 1. Okay, and that gets us to that degrees of freedom. Does everybody follow that? Right, so that's your standard sort of two-sample t-test. Okay, you can get the critical value, or alternatively, you can just evaluate directly the p-value from R. Okay, the critical cutoff value is negative 1.96. Given that our observed test statistic is less than that, then we can say, so visually you can sort of visualize this if you like. Okay, that's your standard t distribution. Okay, your observed statistic is somewhere here. Okay, and your cutoff value is here. Right, and given that the observed statistic is in the lower left tail, we have strong evidence to reject the null. Right? Alternatively, you can just evaluate the p-value directly. Okay, again using R to evaluate the p-value. Okay, so the appropriate function for the t distribution is pt. Okay, t for representing the t distribution, the p stands for probabilities of t distribution. Okay, so the probability of t distribution at negative 26, which is our observed statistic, and you need to provide the degrees of freedom. Okay, now can anyone tell me why do we multiply it by 2? Anyone? Why do we multiply that p evaluation by 2? Sorry? Yep, exactly. Remember, we're carrying out a two-sided test. Okay, this function pt, okay, evaluates the probability of your observed test statistic, the probability that the value is below the observed test statistic. Okay, right. But given that we're doing a two-sided test, it is entirely possible that you could have gotten your test statistic in the right tail. So you need to take both. You need to take into account both the tails. Okay, so you multiply that probability by 2. After you've done that, you'll notice that the p-value is fairly small. Okay, it's almost equal to 0. It's 1.68 to the power 1.68 times 10 to the power 147. Okay, which is basically a series of 146 zeros, then followed by this number. Okay, which is, you can just treat this as being equal to 0. Okay, right. Either way, this t-test tells us that the two group means are not the same, meaning that there is an statistically significant difference between the price, between the log price of a property which is on the waterfront versus a property which is not on the waterfront. Okay, and if the log prices are statistically different, then the price itself will also be statistically significantly different. Okay, so that's your t-test. Now this was a sort of a roundabout way of doing the t-test, because we did it this way based on what you've studied in your earlier stats courses as to how you can perform that test. Okay, luckily for us, R can do that whole entire calculation, okay, with just a simple single function. Okay, the function is called t.test. Okay, fine. The arguments that go to t.test are the two samples or the two groups that you're trying to compare. Right. So in this case, we have the two groups. One is the log price when waterfront is equal to 0, meaning log price of all the properties where waterfront is not there, and log price of all the properties with a waterfront. Okay? Right, so you provide the two samples, the two groups. You specify what alternative you want to test. So we're choosing a two-sided alternative. Okay, and the last bit is typically this is what we mostly choose unless we have strong reason to suspect that the variance of the two groups are not the same. Okay, now for us visually we had just seen using sort of the box plot that the variance of the two groups are not too different from each other. Okay, right? So we specify that condition in our t.test function. Okay, so just employing that single command does pretty much all the work that we did in these last 3 slides, which is first to calculate all the sample statistics, y bar 0, y bar 1, n0, n1, sp, so on, then calculate the test statistic and compare it to a appropriate t-distribution to evaluate the p-value. So all of this can just be done using a single command, t.test. Okay? Notice the outputs provides us with all the information. Right? So it gives us with the test statistic, the degrees of freedom, the p-value. Okay? It also gives us the individual sample means. Okay, notice these sample means are nothing but y bar 0 and y bar 1. Okay, as we got from our more direct evaluation. Okay. It in fact also calculates a confidence interval for the difference. Okay, so that confidence interval is for the is for the difference y bar 0 minus y bar 1. Okay? Does everybody get that? Right? And then based on all of the information that we have in that output for the t.test, we can again come to the same conclusion, okay, which is that the mean price, the mean of the log price of a waterfront property is different from a non-waterfront property. Okay, right? That's your basic sort of statistics. Over here we've not really talked about regression and so on. But now we'll start by first showing you that you can do exactly the same thing, the same test, but using the regression approach. Okay, right? So before we actually look at the whole multiple linear regression context, let's redo this test but using a regression approach, which will also hopefully show you the power of regression in these kinds of tests and analysis. Okay, so first thing we need to do obviously is to create our design matrix, our matrix X, right? Okay, and this is how we are going to do it in this example, right? So here's our actual variable, the waterfront variable, right? It's essentially got values of 0 and 1, right? 1 representing that there is a waterfront, so yes, and no representing 0, which means there is no waterfront. Okay, right? Now our design matrix, our X matrix, is going to have 2 variables. I'll call them D0 and D1. Okay, D0 is used whenever there is no waterfront, and D1 is used whenever there is a waterfront property. Okay, so when we have a waterfront property, so let's take an example of the very first data point, okay, which is a waterfront property because waterfront is equal to yes. Okay, therefore we set D1 to 1 and D0 to 0. Okay, right? So the way we define these 2 variables is that D1 is equal to 1 whenever we have a waterfront property. And whenever we do not have a waterfront property, then we set D0 to 1. Okay, so one thing you'll notice is that D0 and D1 will never both take on the same value. If D1 is 1, then D0 has to be 0. Okay, if D0 is 1, then D1 has to be 0. Right? Okay. So you notice the last observation, which is a no waterfront property. D1 takes on the value 1, D1 takes on the value 0, and D0 takes on the value 1. Right? Okay. This is what we call the dummy variable coding. Right? So we're using dummy variables to code whether a property is waterfront or not. Okay? Right? Now let's look at the regression model itself. Okay? The regression model in this case is beta 0 times D0 plus beta 1 times D1. Okay, so that's our regression model. Obviously you have the error term. Okay, right? And just like our previous assumptions, the errors are going to be normally distributed with zero mean and constant variance sigma squared. Okay, and you can evaluate the estimates for beta using the least squares estimation approach, which we know is given by that matrix formula, right? X transpose X inverse X transpose Y. Right? Again, we'll do it from sort of these first principles using matrix approach, but remember, you don't really have to do it this way, right? We can use the LM command to give us pretty much the same results, but there's a couple of issues that I want to talk about. That's why we're going through this long form approach. Okay, so we create firstly our two variables D0 and D1, right? Okay, notice how we create these variables, right? We're using the if-else command. Okay, the if-else command has a simple structure. First part of the if-else command is the condition that needs to be satisfied. If it is true, then you take on the first value. If it is false, you take the second value. Right? So that's how an if-else statements work. So if the condition is true, then the first value is taken on. If it's false, the second value is taken on. Okay? And that's how we create D0 and D1. Then we combine the two variables D0, D1 into a matrix X. Okay, a design matrix X. The command we use for that is cbind. Okay, cbind stands for binding of columns. So C for representing columns and bind obviously to bind them together. So essentially cbind, the way it works, it takes a series of vectors and combines them into a matrix. Okay. Y obviously is our log price. And then we can solve for beta hat, our least square estimator of beta, using that formula, X transpose X inverse, X transpose Y. Okay, right? In R, if you want to find the inverse of a matrix, you can use the solve function. Okay, that's what that solve function represents over there, taking the inverse of whatever's inside the brackets. Okay. Again, remember, when you're doing matrix multiplication, you do not use the star asterisk to represent multiplication. Matrix multiplication is represented as percentage star percentage. Okay, that's how R distinguish between a scalar multiplication of vectors versus a matrix multiplication. Okay, is everybody clear? Right. Okay. We get the value for beta hat. Now notice the beta hat values. Are they similar to some values that we've just seen before? The beta 0 the beta 0 hat and beta 1 hat that we've got here, okay, do they remind you of some values that you've seen in one of the previous slides? And do they look very similar to y bar 0 and y bar 1? In fact, they are equal to y bar 0 and y bar 1. Okay. Notice if we go back to the t-test, notice the two means, y bar 0 and y bar 1. Okay. In our regression context, they somehow represent beta 0 hat and beta 1 hat. Okay. Does everybody get that? Right? So how does all of this sort of fit in? Right? So we're basically saying that yi fitted value is equal to beta 0 hat d0 plus beta 1 hat d1. Yep. Sorry? We'll come to that. I'll come to that in a couple of minutes. So the question was, why don't we have an intercept term? And I'll come to that question in just a few minutes. Okay. But getting back to this one, so we can see that our regression model, the fitted model, looks something like that. Okay. Right. Which you'll notice is similar to how the t-test is structured. Right. We're looking at the log price as a function of the group 1 mean versus the group 2 mean, and that's what we've done here as well. Right, it's a combination of the two. Right, so the log price of a house is either going to be the mean price of mean price of a non-waterfront property or the mean price of a waterfront property. Okay, right, and taken together, it's in a sense average, a sample mean of the two. Okay, right. So alternatively, what we can do, so rather than evaluating B0 hat and B1 hat, beta 0 hat and beta 1 hat using first principles, using matrices, we can just use the lm command. Right? So we can fit a model. So the model we are fitting is with log price as our response and D0 and D1 as our predictors. Okay, you'll notice that we have used a -1 here. Okay, that is to explicitly leave out the intercept. Okay, remember in this setup we did not have an intercept term. Okay, so that's how you code that into R. When you don't want an intercept term, you use -1 in the lm command. Okay, again, why we choose to not have the intercept, I'll come back in a few minutes. Okay. Anyway, once we run the summary of that model, okay, you'll notice that we can get, again, our coefficients, the estimates of our coefficients, so B0 and B1, okay. We can get their standard errors and their associated t statistics and probability tests, okay. Again, you'll notice the estimates obviously are Y0 bar and Y1 bar. Okay? So, why did we not choose to have the intercept? Okay, so let's say if we went ahead and did include an intercept term. Right? So let's say the model is beta 0 plus beta 1 D0 plus beta 2 D1. Right? So you have the standard intercept included. Okay? Then your design matrix, as you can see here, would have the intercept term, the D0 values, and the D1 values. Okay? D0, D1 are defined just as they were before. D0 represents a property without a waterfront, and D1 represents a property with a waterfront. Okay? right? You'll notice that the intercept term, if you include it here, is nothing, which will always be 1, is nothing but the sum. So the intercept is nothing but the sum of D0 and D1. Is that correct? Right? The intercept value can always be found by summing up the values for D0 and D1. We know that D0 and D1 will either be 1 or 0. They can both never be 1 together simultaneously. They can both never be 0 simultaneously. Okay? Right? So if one of them is 1, the other has to be 0. Right? And so if you take the sum of those two, you always get the value that you have in the intercept. Okay? Which essentially means that this matrix X is now no longer a full rank matrix. Okay? Essentially, it's a matrix which cannot be inverted, right? Which therefore means that this, the solution to that beta, okay, which is X transpose X inverse X transpose Y, is not solvable. Okay? Right? It will not give you a finite value. Okay? Right? That's sort of the mathematical side of it. The other side is basically trying to say, so in a non-mathematical sense, we're basically saying that we have one variable which is essentially a linear combination of the other two variables. Okay? So we essentially have linear dependence here in terms of our three variables, the intercept, D0 and D1. Okay? And notice when we were talking about matrices just before the break, when a matrix has linear dependence in its vectors, in its columns, okay, then that matrix is not invertible. Right? Okay? And practically speaking, what we're basically saying is that this intercept variable is redundant. Okay? It's not giving us any new information. Its information, whatever it provides us, okay, can be easily gleaned from the other two. We don't need the intercept term. Right? Okay? If we just want to talk about whether a property has waterfront or does not have a waterfront, we just need D0 and D1. We don't need the intercept term. Right? Okay? But saying that, we generally do like the intercept term. Okay? It's sort of the convention that we are used to, right? That the intercept's always there. Okay? If that's the case, then let's just redefine how we classify our waterfront variable. Okay? So now, instead of using two variables to represent waterfront, D0 and D1, we'll just use one variable. Okay, so we'll have the intercept term, as we always do, okay, and that's something we are used to. And now we only have one other variable, call it D1, okay, and it is that previous D1 variable exactly, okay, to represent the presence of waterfront. Okay, right? This way of thinking about a factor, okay, is equivalent to sort of picking what we call a reference level. Okay, so whenever you have a categorical variable, so a variable with multiple categories, you choose one of its category as your reference category, as your reference level. Okay, so basically what you're saying is you're going to look at the model in reference to that particular level or that particular category. Okay, in this case, we are saying that no waterfront is our reference level. Okay, right? So we look at all properties without waterfront, that's our reference, and then we add the effect of having a waterfront. Okay, and that adding the effect of having a waterfront is done by including the D1 variable. Right, and the D1 variable, as you notice, represents or takes on the value 1 when there is a waterfront property, and it takes on the value 0 when there is not a waterfront property. Okay? Does everybody get that? Right, yep. Full rank in mathematical sense essentially talks about that a matrix, the columns of a matrix are all linearly independent, meaning that any one vector, any one column cannot be written as a linear combination of the other columns. Okay, so this one over here, so this matrix here does not have a full rank because one of its vector, the intercept vector, can be written as a linear combination of the other two. Right? So that's a matrix of less than full rank. Okay? A matrix would have full rank whenever its rank is equal to the number of columns it has. Okay? Right, so now this model representation is something we're more used to, right? We have our intercept and we have our predictor variable, okay? And then we can obviously write our model in a more predictable way, right? Which is that our model has an intercept term plus our variable, our predictor variable, with its coefficient beta 1, okay, and then the error term. Right? Okay. How do you interpret this model? Okay, we interpret it in the sense that whenever D1 is equal to 1, meaning when we have a house with a waterfront, okay, then our fitted model looks like this, right? Which is yi is equal to beta 0 plus beta 1. Obviously D1 is equal to 1, so we just have that, right? So yi hat is beta 0 plus beta 1. Okay? Similarly, when D1 is equal to 0, meaning the house is not a waterfront house, okay, then our model becomes yi hat is equal to beta 0 hat. Okay? The beta 1 hat term disappears because D1 takes on the value 0. Okay? Does everybody get that? Right? So in this instance, in this representation, beta 1, our estimate for the slope coefficient, okay, represents the change in log price for a house having a waterfront. Okay, so in one sense you can think of beta 1 as the value added to the property price, okay, because of having a waterfront. Okay, although I'm using the word value added, okay, it could be negative, right? If beta 1 is a negative, if its estimates is negative, then it's still an addition, but it's an addition of a negative value. Okay? Does everybody get that? Okay. So this way of representing a model with a categorical variable makes interpretation much easier and much more sort of intuitive to follow. Okay? We basically have in the absence of the categorical variable, in the absence of a waterfront property, okay, we say that our fitted response value, meaning our log price, is equal to the estimate of beta 0 hat. Okay, but when we do have a waterfront property, it has an addition of beta 1 hat in terms of value added. Okay, right? So if we talk back in terms of the means, right? So notice how when we were using the D0 and D1 as our two predictors, okay, we got beta 0 hat as y0 bar and beta 1 hat as y1 bar, right? Okay. Again, notice how this all fits in. Looking at our model here at the top, if you have a non-waterfront property, which would mean that D0 takes on the value 1 and D1 takes on the value 0, okay, your fitted model essentially is y bar or y hat is equal to beta 0 hat. okay? Because D0 is 1 and D1 is 0 for a non-waterfront house, okay? For a waterfront house, we would have the exact opposite condition, right? Which is D0 would be equal to 0 and D1 would be equal to 1. And so you would have Y hat as B1 hat. Okay, and that's why you notice that the estimate for beta 0 hat is Y0 bar, and the estimate for beta 1 hat is Y1 bar. Okay, the two sample means, the two group means. Now, in this are sort of the standard approach of writing a regression model where we have an intercept term. Over here, the intercept term represents our reference value, our reference category, meaning it's the house with a non-waterfront or it's a non-waterfront property. Okay, therefore Y hat would be beta 0 hat, and this we would expect to be equal to Y0 bar. Okay. Right? And so when we do have a waterfront property, our fitted model is, so is Y hat is equal to beta 0 hat plus beta 1 hat. Okay? For a waterfront property, we would expect Y hat to be equal to Y1 bar. Okay, the group mean for all the waterfront houses. Okay, but we've already expecting beta 0 hat to be Y0 bar, and so we would have beta 1 hat to be Y1 bar minus Y0 bar. Okay, in another sense, it's the additional value over and above the reference category, the reference level. Okay, so beta 1 hat now measures how much value is added on to the log price in this instance when you have a waterfront property, okay, which is represented as the difference between the log price of a waterfront property minus the log price of a non-waterfront property. Okay, right? So this is what we would expect. Let's see, in fact, when we run the model, do we get that same response? Okay, notice the estimate for the intercept is 13.039, okay, which is equal to Y0 bar. Okay, right? We can go back a couple of slides and confirm. Okay, same. Right? But now the estimate for D1, so beta 1 hat or beta 1 hat is equal to 1.062. Okay? And this, you will notice, would be equal to Y1 bar minus Y0 bar. Okay? Right? In fact, if we add these two together, the two coefficients together, we must necessarily get Y1 bar. Okay? And that we can see in this command that I've given at the bottom, the sum of the coefficients of our model, okay, you'll notice is equal to Y1 bar, which is 14.102. Okay? Does everybody get that? Right? Now, more important for us is essentially performing the same test as we did before, right? The way you would now carry out that same t-test is look at this t-test statistic, okay, and its corresponding p-value. Notice how the test statistic is just like the one that we've seen previously. Okay, the observed test statistic is about 26, okay, and its corresponding p-value is almost equal to 0. Okay, and therefore, again, this test tells us or gives us the same result as before, which is it is testing whether the null of mu0 equals mu1 versus the alternative mu0 not equal to mu1. Okay. In terms of regression, we write it slightly differently. Okay. In terms of regression, that test statistic is for the fact that beta 1 is equal to 0 versus the alternative that beta 1 is non-zero. Okay? Does everybody get that? Right? But notice how beta 1 and beta 0 are constructed. You're essentially performing the same test. Right? Okay? But this particular way of writing out this test, so using regression to perform this test, has additional value. Okay, we are not just performing a single t-test of comparing the means, okay, but in a sense we are also quantifying what is the difference of a waterfront property versus a non-waterfront property. Okay, we are basically saying that for having a waterfront property increases the log price of the mean log price of the property value by that amount. Okay? Right? A non-waterfront property has a mean log price of 13.039. Okay? But having a waterfront property adds to the value of that log price by a factor of about 1.06. Okay? Right? Does everybody get that? Okay? That's just having one qualitative variable, okay, but now let's add a few more predictors, okay, and that's where the actual benefit of regression comes in, okay. Remember, the t-test that we performed at the very beginning is limited to just that. It can only compare the group means of a non-waterfront versus a waterfront property value, okay. It cannot much tell us about the individual characteristics of those houses, right? Whether we are comparing big houses to small houses, so on and so forth, right? Okay. One would sort of, you can pose a question, something like that. You would expect that waterfront properties would be larger in size. Okay, given that waterfront properties are more expensive, people would tend to build larger houses because people who can afford those houses will want to build bigger houses. Right? So one way of explaining the difference between a waterfront property and a non-waterfront property in terms of its prices, okay, is all to do with the area of the house and not the fact that there is a waterfront. Okay? Does everybody sort of get that explanation? Okay, so one way you could reason out why waterfront properties are more expensive is because of the actual house size, not because of the presence of a waterfront. Okay? So one way to test that would be to run a regression where you have waterfront in your regression, but you also have the living area in your regression as well. Right? So you essentially control for the square foot living area. Okay? If you have that in your model, and if still waterfront turns out to be predictive, meaning statistically significant, okay, then we can reasonably say that after controlling for the living area as well, waterfront does improve the value of the property. Okay? Does everybody get that? Right? If after fitting living area, it turns out that waterfront is not statistically significant, okay, then that supports our initial assumption, which is that property prices are majorly driven by just the living area and not the presence or absence of waterfront. Okay? It just turns out that most properties which are on a waterfront are larger and therefore more expensive. Right? Okay, so we're trying to test that, okay, by having living area included in our model. Okay, so that's the next model that we're trying to assess, given there at the bottom, right? Notice we now use our intercept as a standard, right? So beta 0 is our intercept. Beta 1 times D1 represents the presence of a waterfront house, okay? And beta 2 represents the living area coefficient, okay? And following on from last week, we use the log of the living area and not the actual living area, okay? We've already seen in the previous week, log of living area is a better predictor. It makes the relationship linear, more linear. Okay? Does everybody get that? Right? So, in a sense, what we do see here is that if you have a property which is a not or a non-waterfront property, meaning D1 would be equal to 0. Okay? So for a no waterfront property, your model is yi equals beta 0 plus beta 2 log living area plus epsilon. Okay? But if you do have a living waterfront property, or if you have a property with a waterfront, then your model becomes yi equals beta 0 plus beta 1 plus beta 2 log living area. Okay? So that's essentially the two models that we are fitting, okay, within that single representation. Okay? Now if you were to plot this as a scatter plot and and plot the models itself as lines, what would you expect? Looking at these two representations, you notice that the slope is the same in both the models. Okay? What is changing is the intercept term, the intercept of the line. Okay? The one which has a no waterfront has a particular intercept given as beta 0, but a property which does have a waterfront has a different intercept given by beta 0 plus beta 1. Okay? So let's in fact visually confirm that. So we plot our log of square foot living versus log of price. Okay, living area on X, log of price on Y-axis. Okay, then add the points. Okay, now in this case, what we're doing in those two lines at the bottom, what I'm doing is adding points of different color. Okay, so cyan, blue, would represent no waterfront, and orange would represent a waterfront house. Okay, and if you look at that, we get to see all our points. Right, so all the blue dots are properties without any waterfront. Okay, and all the orange dots are properties with a waterfront. Okay, now let's add the two models, the linear model to that. Right, so we'll first fit it. Okay, so now our model represents log price with D1 and log square foot living. Okay. Take the summary and you get the estimates. Okay, remember these are estimates for beta 0 hat, beta 1 hat, and beta 2 hat. Right? Okay. And then if we add those lines to our previously fitted scatter plot, okay, again we'll add an orange line for the waterfront houses. Okay, and an orange line for our waterfront houses and a blue line for our non-waterfront houses. Okay, that's what we have done here at the bottom. Okay, does everybody get that? Right? And we get our two models. Okay, and as we can see, we do get two lines with the same slope. They're parallel to each other, but with different intercept. Okay, the intercept for the orange line is beta 0 hat plus beta 1 hat. Okay, whereas the intercept for the blue line is just beta 0 hat. Okay? Right? How do you interpret this model? We're basically saying that price of a property increases with log of square foot living area as given by the sloping line, okay? But the price of the property is also dependent on whether the property has a waterfront or not, okay? On average, prices of the waterfront properties are going to be larger by a factor of beta 1 hat than the ones without any waterfront. Okay, so if you look at two representative or two sample houses which have the same living area, draw that in red. So you're looking at two houses which have the same living area, okay, then their prices will differ by, on average, by the amount beta 1. Okay, and that's the effect of having a waterfront. Okay, although they have the same living area, the waterfront house on average is still more expensive. Okay, and that shows us that we've also sort of controlled for the living area. Okay, so that initial hypothesis that I had put up, which was that houses only truly depend on the living area and not the presence or absence of waterfront, we can test that. We can test that as a sample, as an hypothesis by testing to see whether beta 1 is equal to 0 or not. Okay, so a test statistic can be carried out, or a test can be carried out for the hypothesis that beta 1 is equal to 0 versus beta 1 not equal to 0. Okay, and you can do that based on, if you look back to our summary model, we can do that based on the corresponding t statistic, right, or the t-test. Okay, remember the test itself and its structure is just like it was before, right? The hypothesis is beta 1 equals 0 versus beta 1 not equal to 0. Okay, the test statistic is beta 1 hat over standard error of beta 1 hat. Okay, which gives us this test statistic here, 24.53, and its corresponding p-value. Okay, does everybody get that? Right? Yet another way of doing this test would be to use the f-test, right? Which would mean using the ANOVA, right? But be careful. Just like what we discussed last week, ANOVA for multiple regression, the order in which you fit the variables is very important. So if you want to do a test for D1, okay, then you must have D1 as the last variable fitted when you run the ANOVA command. Okay, and then you can use the corresponding f-test from that ANOVA output to perform the same exact test. Okay, currently as it stands, as this model stands, the f statistic that is given at the bottom, okay, is in fact to test log of square foot living area after or conditioning on waterfront being fitted in the model. Okay, does everybody get that? Right? Any questions? Nope? Okay. Now, let's add a little bit of more of a complication. Okay? Over here, we assumed, so in the previous model, we assumed that the effect of square foot living area is identical, irrespective of whether the house has a waterfront or does not have a waterfront. Okay, and the only effect that we are measuring is having a waterfront, right? Which, in graphical terms, was equivalent to saying that the two lines are parallel to each other. Okay, but they have, so Parallel meaning they have the same slopes, but they have different intercept, meaning they have a different sort of a starting point, okay? A different base point to begin at, right? Okay. What if we want the price to not just depend on the waterfront, but also the combination of waterfront with the living area? Meaning we want the slopes to also be different. Okay? Meaning, or spoken another way, we're basically saying that properties which have a waterfront have a slightly different relationship to the square foot living area versus properties that do not have a waterfront. Okay? So the relationship between price and living area is no longer the same. Okay? It will depend on whether there is a waterfront or not. Okay? In this particular setting, you'll notice the relationship between log price and log living area is constant, is fixed, whether there is a waterfront or not, right? Because both of them have the same slope given by beta 2. Right? Beta 2 measures the relationship between log price and living area. Okay? But now we want to say that we want that relationship to also change, right? So in a sense, we're basically saying those properties which have a waterfront, we expect that their relationship to price will be different. Okay, so their price will change in a different manner as compared to the square foot living area. Okay? Statistically or mathematically, what we are going to do, therefore, is add what we call an interaction term. The interaction between square foot living area and having a waterfront. Okay? So mathematically speaking, we have this extra term now. Okay, notice the rest of the model is just like before. Okay, beta 0 plus beta 1 D1 plus beta 2 living area, log living area. And now we have a new term, beta 3 times log living area times D1. Okay? Right? What this essentially means is if you have a waterfront house, okay, for a waterfront house, D1 would be equal to 1. Okay, and therefore your new intercept would be beta 0 plus beta 1, and your new slope would be beta 2 plus beta 3. Right, beta 2 comes from that part, fitting square foot living area. Beta 3 comes from the interaction term. Because D1 is equal to 1, we have log living area times D1, which is essentially 1, and therefore you have beta 3 added on. Okay? But if you don't have a waterfront property, meaning D1 would be equal to 0, you would have slope as just, intercept as just beta 0, because D1 is equal to 0, as well as the slope is also just beta 2. Again, because D1 is equal to 0, we have a non-waterfront property. Okay, so an interaction term, as I just said before, would lead us to have two lines now with both different intercepts and different slopes. Okay? Does everybody get that? Right? So how do we fit such a model in R? Okay, the command is quite straightforward. So you obviously include D1, your categorical variable for waterfront. You include log or square foot living area. Okay, but then you add the interaction. The interaction is denoted using or combined using the colon. Okay, so D1 colon log living area. Okay, which looks at the interaction of these two together. Okay, Does everybody get that? Right? And so when we get the summary of that, we would get our four estimates, right? So we have beta 0 hat, beta 1 hat, beta 2 hat, and beta 3 hat. Okay? Does everybody get that? Right? Now, keep in mind, when you're actually doing regression with an interaction term, you should always first test the model without the interaction, okay? And then have the interaction added on, right? Or one way to do that is fit the model with the interaction term, see whether the interaction is significant. If not, you remove the interaction term. Okay? Right? So the idea is you test first to see whether you can do with different slopes and different intercepts, whether those are required. If not, you revert back to having same slope but different intercept. Okay? Right? Again, testing that is fairly straightforward. It follows, again, the same approach as you've done before, right? In this case, you would look at that last line and look at its corresponding t-value and the t-statistic and the p-value, okay, to assess whether the interaction term is statistically significant. Okay? Keep in mind, again, I spoke about this last week, but I'll reiterate it again here. When you're using the t-statistic, okay, it is always under the condition that all the other predictors are in the model, are held constant, are held fixed. Okay, so this test statistic here, which does give us a t-statistic of 4.69 and a p-value of approximately 0, much less than 0.05, okay? It's under the condition that all the other three are in the model. You haven't removed any one of them. Okay? Does everybody get that? Right? Alternatively, you can just do the F test using ANOVA, okay? Making sure that the interaction term is fitted last, and then look at the extra sum of squares for that to assess whether the interaction term is significant. Okay? In this case, in fact, given that we have fitted the interaction term last, we can look at the F statistic given at the bottom, okay, to tell us whether that is significant or not. Okay? So in this case, we do see that the interaction term is significant. Okay? Which means that having different slope, different intercept does in fact, or is in fact a better model than having same slopes but different intercept. Okay? We can visually also see this. Again, going back to that previous scatter plot, now we add lines to that model where the slope and the intercept both change. Right? Again, the orange line would represent the line for with waterfront properties, and the blue line represents the properties without any waterfront. Okay? I notice the slopes not vastly different from each other, but they are different. Okay? The lines are no longer parallel. Okay? Right? In fact, the width waterfront property have a larger slope, which sort of suggests that the price increase in a waterfront property is much more faster in relation to the living area as compared to a non-waterfront property. Right? Okay? So for example, if you have two comparable houses, okay, one on a waterfront, one without a waterfront, okay, then a unit increase in the area will increase the price of the waterfront property much larger than the non-waterfront property. Okay, the increase in the waterfront house would be quantified as beta 1 plus beta 3, sorry, beta 2 plus beta 3. Okay, whereas the increase in the non-waterfront house would simply be beta 2. Okay, so having a waterfront increases the value of the house by increasing one unit area of the house itself, okay, by amount beta 3. Does everybody get that? Right. So, as I was saying, to test these sort of added on relationship, we need to ensure that when you're looking at the ANOVA results, you do it in the right order. Okay? So in the first setting that we have, right, as we had set up our model, okay, we had fitted D1 first, then log of living area, then the interaction term. Okay? In this instance, okay, this ANOVA table is useful in testing whether the interaction term is significant or not. Okay? That last sum of squares, and therefore its corresponding F value and its probability or P value tells us whether the interaction term is significant. Okay? This tells us, in fact, that it is. Okay? The F statistic is 22 with a P value of less than 0.05. Okay? Suggesting that the interaction term is statistically significant. Now notice this F statistic is the same as we got in, it's same as you would get by squaring this T statistic for in our summary results, okay, for that interaction term, right? So, but now if you want to study the effect of waterfront property as a whole, not just the interaction term, but the having a waterfront as a whole, it would mean we want to test the coefficient for D1 and the coefficient for the interaction term with D1. All right? That would study the effect of the in totality of the waterfront. Okay? Meaning whether having a waterfront does increase the price of a property in a statistically significant way for both, in terms of both the intercept as well as the slope. Okay, so if you want to do that, then this ANOVA table is not really helpful because we have sort of that log square foot living area fitted in the middle. Okay, so we can revert or change the order slightly. Okay, so first have log square foot living, then have D1, and then the interaction. Okay, if we do that, then we can now use this ANOVA table, okay, to carry out that same test. Okay, so the test that we now want to carry out is to test whether beta 2 and beta 3 both are equal to 0 versus the alternative that at least one of them is non-zero. Okay, in this case, notice beta 2 is for D1, beta 3 is for the interaction term. Okay, and we've changed the order. So test statistic again, okay, you take the last two sum of squares, add them up, divide by the sum of the degrees of freedom, okay, divided by the mean squared error. Okay, so that's what this essentially formula is talking about. Right, it's the sum of squares for, so that's sum of squares, extra sum of squares for waterfront. That's the sum of squares for the interaction term, added up, divided by both their degrees of freedom, so that's 2, divided by mean squared error. Okay, so that's just mean squared error for the full model, the large model. Okay? Giving us an F statistic of 312 approximately. You compare that to an appropriate F distribution with 2 numerator degrees of freedom and n-4 denominator degrees of freedom. Okay, giving us a p-value which is approximately 0. Okay, and that would give us the results. Okay. Again, what we discussed previous week as well, if you don't really want to worry about the ordering of the models and so on, okay, you can do that as well. You just fit two models, okay, one which is your small model, which does not have the added terms, so D1